hole mobility and high electron mobility, then we can get a good performance device. We can get it. So this is just that we have already talked about this. How is it electrons and holes and emitting at emissive layer? Here the emissive layer is the quantum dots. Okay, the first transporting layer we are talk about this electron transporting layer. This is actually help electron transport from electrode. Because electrode, we did say cathode to anode is sometime, where we are going to connect. It might change. So it's to transport to emissive layer. So this is N-type material typically used for making ETL electron transporting layer. So this has to be high mobility, high electron mobility, and high triplet energy to enhancing the device performance. Right, ETL materials have non-zero permanent molecular dipole moment. They should have that. So this is, I summarize again, the high electron transport mobility, and this is high class transition temperature. It should be expecting greater than 120 degrees. And thermal stability withstand during the QLED or OLED operation. Maybe sometime heat is created when we are applying the current, so that it should be thermal stability, all those material. Then that's the important thing is the processability, that making the pinhole free thin films by the BT or spin coating printing technique. This is I'm going to talk about in the next 1 hour lecture. Okay, this is we have normally used mainly for this OLED device. We use ALQ3, TPBI, but often it's normally we use for the as a electron transporting layer in OLED devices. And the QLED devices we mainly use zinc oxide or magnesium, aluminum, gallium oxide, mainly used for making these QLED devices for these electron transporting layers. And this is OLED devices. Mainly there are different type of the ways is we can't use it because the lifetime is the critical part in the device manufacturing. The next one, the whole transporting layer. The whole, like electron transport, here the whole transporting layer is transport holes from one of the electrode and to the emissive layer. So quantum dot light emission, while the zinc oxide nanoparticle layers provide effective electron injection. So into quantum dot layers, the whole transporting material usually cannot currently sufficient cause injection or the deep valence band of quantum dots. So there we have in the OLED side, we don't have a problem for the whole transporting layer, but in QLED manufacturing, we have a problem in the whole transporting side because we have a good electron transporting material, which is zinc oxide and the other metal zinc oxide. So this is one of the structure, the quantum QLED structure here. So this is the inverted structure. You can see this anode, then electron transporting layer with anode, so with the substrate. So this one is inverted structure. Then we are using that quantum dot as a emissive layer. Electron blocker, we got to use it because this when we use zinc oxide, is a high electron mobility one. Electron might pass through before the whole reach to the emissive layer. So we need to block that electron to pass. So we have some material that's that's the best one, TCTA we use, but it might be there are some different materials available using as electron blocking layer. So we can block the electron pass through there. We use 10 nanometer, less than 10 nanometer. So then it could make a good device. Then the whole transport, the alpha and HTM14, these are the small molecule organic materials. And HAL, the whole injecting layer, we use HCNO, MO3, molybdenum trioxide. So here the P-type material, normally that whole transporting layers. So if we use conventional method, we can use P dot, because P dot is normally can be a solution process one, and poly TPD is a whole transporting, is a whole injecting of whole transporting P dot PSS can be used, and poly TPD, TFP, PVK. These are the polymers, alpha and PPVK. It is from the Merck. It is only the research purpose. It is high quality. I mean, research purpose, they are only giving to us. It's not commercially available at the moment. Now, just I'm showing one of the performance we made in the inverted device structure using the electron zinc oxide as a different zinc oxide, the dope zinc oxides as a ETL. And when we use aluminum dope zinc oxide, it gave high performance. It's a high performance. We use here quantum dots as cadmium-free one. Cadmium-free one is still in infant stage, is not commercialized yet. So we got, compared to other ETL, the aluminum dope zinc oxide, we got high performance. This current efficiency is 5.8 and the power efficiency is 3.7 lumens per watt we got from that. Okay, we now move to quantum dots. Okay, quantum dots, you know, that's already I talk about the first day, but still I will go through again. So quantum dots is like it's an inorganic dots. Okay, we use inorganic, all inorganic materials. So this the core, shell, and the ligand. It's made like this. This is type of core, shell, ligands. So this is the quantum dots. So the core size is going to define the colors. It's from 2 to 6 nanometers. If the core is 2 nanometer from the same material, that it might be the rare blue. Then when the size is increased, it can be go through to red. So it is tunable, easy to tunable to different colors. So the quantum dots are semiconductor nanoparticles comprised of 3 engineerable structural components. That core is 2 to 15 nanometer. We can make it to diameter. So the shell is protected and passivate core. So actually the shell is another semiconductor that is protecting the core. Then we use the ligand, Service bound ligands. So this is the 3 parts about these quantum dots. This is one of the paper I just took, but we didn't make, I'm not making any quantum dots. So this is the procedure for the synthesis procedure for the indium phosphide, zinc sulfide, indium phosphide, which is the core, and the zinc sulfide is the shell. Quantum dots procedure, how to make it. Yeah, that and the size, it says the same here. That size is tuning the color. Okay, that what is actually core do, what is the shell do, and but the ligand does for this in quantum dots. So if we take about the core, the size is 2 to 15, and the shell protected is already talk about. Okay, that the core is a size, shape, and composition is determine the absorption and emission wavelength. So when it is change the size and shape and the composition, it will define the absorption emission spectra. So that it's depend the color. It's really defining the color of the size. And the shell thickness, actually shell thickness, actually it is playing the big part in the device side. And the thickness decide the performance of the performance and the wavelength, the full width, half maximum, we will talk about later. That this is that quantum dot cell Then the ligand. Ligand is actually when we disperse in that solvent, it's help us to make a good film. So this is it's using different aliphatic, organometallic, and inorganic molecules, and this is actually is functionalize the semiconductor surface. So it is actually help to make a good the ink. The ligand is actually making a processability. It's actually help to the processability of making the thin films. So this is just the TEM of that quantum dots, and there are different shape of quantum dots. We are going to see it. So this is the brief history of the quantum dot technology. Okay, in 1980, that first cadmium sulfide they invented. Then they use cadmium. Then the cadmium selenide also they used. They make actually the ink. In the 90s, they made that high quality cadmium selenide, cadmium sulfide, cadmium beryllium collided that they make that dispersion. Then actually, really, they work on 2013. 2013, actually, they're commercializing the quantum dots, and still in 2021, they make LCD TV with QD filter. So I have already talked about this application, so I'm not going to talk about anything now. Okay, why need quantum dots? That's important. We have already a good technique. I mean, the OLED technique is there for display, but still we are improving because that emission bandwidth, the full width half maximum, we need less than 20 nanometer. If you see here, this is that the bold one is for the quantum dots emission spectra, and the dotted line is the OLED. The OLED one is, you know, the full width half maximum is very large compared. This is very narrow one. So we need to make a saturated colors. We need a narrow full width half maximum. And you can see this is the OLED. We can achieve these colors up to these colors maximum. But if we use the QLED, we can go up to the saturated red, green, and blue. And also we can, it's easily tunable, but you know, we can use indium phosphide, also cadmium sulfide as a core, but we can tune that color easily. But when the OLED, we need to use different phosphorescent or fluorescent material to make the different colors. And the brightness here, we can get a good brightness. And if you look at the QLED over OLED, the merits means is a good optical characteristics and color quality, color gamut, and saturated color, simple solution processability. So only that organic we have a problem is mostly we have to evaporate, vacuum thermal evaporation is a very high expensive method, and we need right equipments or high vacuum we need. But here we just use this solution processability. Solution processability. So even we can use for the flexible display application is and the large display also we can use it. Okay, this is that current status of okay, this cadmium, there are cadmium based and cadmium free that I don't think it is important at the moment, because the cadmium based one, we can't use it for commercialization. We must use the cadmium free one because of the restriction of the European Union. So this is the different shape of that quantum dots. These rods, plates, branched one, hollow, nested, stripped, barbell or something. But we are going to use that Ola normal round one. We use we use a quantum dot like these ones. This is the zero dimension, 0D ones. That emission is, we can full width half maximum is 20 nanometer. This is a little bit more, and this the 2D quantum well one, it is a 10 to 20 nanometer. This and cadmium-free can be made from here. In the quantum wires wrote, these two is very difficult to make using the cadmium-free one, and this also is challenging. Only this one can be used because we need to use cadmium-free quantum dots for commercialization. So this is the heavy metal one, is a cadmium-based one. You can see the cadmium selenide is covering all the colors, all the spectral wavelengths is from 450 to 652. We can tune and we can get all colors from that. There are other ones, and it's deep red. It is lead sulfide, lead selenide also. But this is the so far is the best one, but it can't be used for commercial appliances. So we look for the metal-free quantum dots. That's metal-free is mainly, we looked at the most suitable one is the indium phosphide one. But indium phosphide, we can't make any blue emission. That's spectral wavelength is from 530 to some 750 to the deep red. But so then the zinc selenide is another option to make the blue emission only as a core for this heavy metal free quantum dots. So this is what the toxic, it should be less than 100 ppm, and but that's why we can't use the cadmium based one. This is a narrow emission, but it's a advantage in narrow emission, high quantum efficiency, high stability, the cadmium based one. But indium based one, the quantum efficiency is low and difficult to blue emission, but still there are some options. Zinc selenide can used, but still that performance is not good for the commercialization. So this is that time frame. I think the time is getting short. So I'm just passing through this one. Is the cadmium-free indium phosphide quantum dots? How is it make it, and how far we approach is. We could make red is the good lifetime and performance, but still the green and blue is not enough to commercialize. This okay, and that other things we can improve that performance. We need to ligand exchange. There are the ligands. The ligand is one part playing for this. Performance of the QLED devices. So we need to change the ligands. If we use some longer ligands, then good stability or solubility in the general organic solvent. So this if you use the longer ligands, it might make stability of the device and solubility in the solvent, or this dispersibility. Actually, it's not going to soluble, it is going to dispersible in that solvent. Then we can make a good film, and also that we can drive with the short circuits. It reduces the energy barrier and increase the electron hole mobility. That's the leading to long life. There are a lot of things to compromise to make good quantum dots. Then we can make good QLED devices. So this is synthesis of quantum dots. Okay, that's all from me for the first season.
Professor, can you hear me?
Yeah, I can hear you.
Yeah, so really thank you, and it's a detailed explanation about this, fabrication side. Actually, we are lacking of fabrication, but you
Yeah.
have given
Okay.
a detailed explanation and what required for doing of real practical application device.
Yeah.
So thank you so much. But if any questions, participants, if you have any other questions, please you can unmute and directly interact with us. Faculties, research scholars, friends, have any questions or clarification? Maybe one or two. Those who are in YouTube, you can also raise the question in the chat box so that we'll synchronize and interact with the experts.
Hello.
Hello.
Yeah, yes, sir.
Yeah. Good afternoon, sir. It's
Good
my
afternoon.
lecture.
Sir, please introduce yourself and then.
Myself, Dr. Pragati Kumar from Central University of Jammu, India. So, sir,
Hello.
I am also working on quantum dot LED and trying to fabricate it. Yeah. So, you are talking about the transparent electrode. So, what is the optimized thickness for the AG to be transparent?
For the emissive layer, or which layer you are talking about?
So, for cathode or means cathode or anode, silver should be transparent.
Oh, the cathode anode. We use the anode. Anode is normally ITO. Which one you are using for that?
Yes. I am using ITO, but if
ITO,
I want to use
that we
silver,
can use 120 nanometer thickness of ITO. That's about 10 ohm per square meter resistance. And cathode, we are using aluminium. Mainly we talk about aluminium. Aluminium is about 100 nanometer thickness we used. That's a vacuum thermal evaporation. Yes. And any other question?
Actually, sir, I am asking if I want to use silver as an anode. So, what should be the optimized thickness for the silver to be transparent?
Transparent. So transparent maximum 10 nanometer for silver.
Maximum. Okay.
Yeah. Then you can mix with the chromium, 1 nanometer chromium. It make more contacts. Sometimes silver is not very attached with the EIL or whatever the top layer. So if you use 1 nanometer chromium, then use some 10 nanometer silver. That's enough for best. Say it's 70% efficient from the light. Sometimes you can't get 100%. It will be refractive that light somewhere, isn't it? So if you use 1 nanometer chromium, then use 10 nanometer silver. It's the best. We found that that's the best for the transparent electrode. The top electrode.
Okay, sir. So, sir, you are working on OLEDs or QLEDs also you have explored?
Yeah, we worked until 2018 OLED mainly. Now fully OLED, QLED, quantum light emitting diodes. And indium phosphide based, not cadmium. Cadmium is we can't use it.
So, sir, is there any possibility to collaborate with you and to visit your institute to do work in your institute for the same QLEDs?
Yeah, actually, you can contact me. We will send you the detail.
Okay, thank you, Rama sir. Thank you.
Thank you.
Yeah, Arisha, are you raising the questions? If you have any doubt, please unmute and then interact. Arisha, you can unmute and then interact. you were raising question actually, but if you have any question, you can also type. Okay, so I think, yeah, sir, shall we take a 5-minute break?
Yeah, that's fine. Yeah, thank you.
Yeah, so the next hour will be going to handle by Professor Pongaral sir only. So if you have any other doubts, you just keep it with you and we will discuss later.
Thank you. See you in 5 minutes. Yeah.
Yeah, yes, sir. Another 5 minutes. Yes.
Yeah.